The last type of function we're going to study is the logarithmic function. And the logarithmic function is the inverse of the exponential function. So we're going to build up our log functions from our knowledge from exponential functions. So we're going to start with graphing the exponential function with base 2 and initial value of 1. Basically just f of x equals 2 to the x. Okay, so let's say that this function computes the number of bacteria after x hours, and we're going to use a table of values to draw the graph of the exponential function. So when x is 0, since x represents hours, we're going to start with 0. The output is going to be 2 to the 0, right? The y value is computed like that, 2 to the 0, which is 1. When x is 1, the output is going to be 2 to the 1, which is 2. When x is 2, the output is going to be 2 squared, which is 4. And when x is 3, the output is going to be 2 to the third, which is 8. So we're going to plot these numbers, 0, 1. So 0 for x, 1 for y, 1 for x, 2, 1 for x, 2 for y, 2 for x, 4 for y, and then 3 for x, and 8 for y. So this is giving us enough points to kind of draw the exponential. So this is f of x. And if x did not represent hours, then we could have also this other portion of the graph. But since x represents hours, it doesn't make sense to have -1 hours or -2. So that's why we're looking only on this portion of the function x. So now if you look at this function f of x and you're asked to draw the inverse, first of all, is this function 1-to-1? Does it have an inverse? So recall that for a function to be 1-to-1, it has to pass the horizontal line test. So if you draw a horizontal line, it only intersects the graph into one point, so then it means it has an inverse. And remember how to get the inverse if you have the graph of a function? You basically reflect the function f over the line y equals x. So to get the inverse of the function f, I'm going to reflect this portion over the y equals x. So basically the point 0, 1 becomes the point 1, 0. So the input is going to be 1 and the output is going to be 0. Remember that when you have the inverse function, it basically takes as input the output of the f, and it takes as output the input. So then the next point will be, let's just put all the 0, 1, 2, 3, that's the input of f, so it's going to become the output of y, of the inverse, I'm sorry. And then 1, 2, 4, 8 is going to become the input. So the next point will be 2, 1. So 2 for x, 1 for y, 4, 2, 4, and then 2, and then 8, and 3. So basically, reflected over the y equals x is going to look like this. So this is the function f inverse of x. And if we wanted to reflect this portion that doesn't make sense in the context of our problem, it would go in here. Okay? So f of x is the exponential, 2 to the x, and then its inverse is this function, okay? Now we gotta think about this inverse. So the input of the inverse was the output of f, and then the output of the inverse is the input of f. So basically, this inverse has to have a name. It has its own name, and it's called the logarithmic function. So if you have f, and f of x is 2 to the x, is the exponential function with base 2, its inverse is going to be called the logarithmic function with base 2. And this is how we write it. We write it as log base 2 of x. Okay, so This is how we are going to start talking about the logarithmic function. We are going to relate it to the exponential function. So if you have your f of x equals 2 to the x, it's exponential function. This is the same as saying 2 to the x equals, your f of x is the same as the output, the y value, right? Then the logarithmic function, we don't have another notation for logarithmic, so we simply decided to just write it log base 2. So now, since it's the inverse of the f function, it's going to switch the input and the output. So the input of f is going to become the output. So x goes here, and then the output of f is going to be the input of the log function. What I'm saying here basically is that saying that 2 to the x equals y, in logarithmic form, this means that logarithm of base 2, so it keeps the same base, of y equals x. So basically, the logarithmic function is an exponent. Look at here. Log base 2 of y is a number. And if you look in the exponential form, it's the exponent of 2. So let's look at a specific example. If you have 2 to the 4th, that equals 16. If I wanted to write this in logarithmic form, this is going to be log base 2 of 16 of the output equals the input. So this is just saying that I'm looking for a number. The result for log base 2 of 16 is 4 because 2 to the 4th equals 16. Okay, so the result of a log is basically an exponent. It's the exponent. It's the number that the base has to be multiplied by itself to get this value. So we will refer to this. So log base 2 of 16 equals 4 because 2 to the 4th equals 16. So let's look at these exercises here. So I have log base 2 of 32. So basically the result is going to be how many times do I have to multiply 2 by itself to get 32. So basically I'm saying 2 to what power gives me 32. So the answer to log base 2 of 32 is just the exponent that 2 will need to have, such that when evaluated, it gives you 32. So 2 to what power gives me 32? Well, I know that 2 squared is 4, 2 to the 3rd is 8, 2 to the 4th is 16, and 2 to the 5th is 32. So basically, the power we're looking for is 5. So since 2 to the 5 is 32, that means that log base 2 of 32 is 5. Now, for the next one. Log base 2 of 1/2 equals what? So I'm looking for the base is 2. 2 to what power gives me 1/2? Well, 2, we know that 2 to the negative 1 gives you 1/2. Remember negative exponents? So 2 to the negative 1 equals 1/2. So therefore, logarithm of base 2 of 1/2 equals negative 1. Now the base is 10, number 3. Log base 10 of 100 equals what? So this translates into 10, the base, to what power gives me 100? Well, I know that 10 squared means 100. So log base 10 of 100 equals 2. So if you notice, every time we have a log, to evaluate a log, we're basically going to think about the equivalent exponential form. Because we are more comfortable with exponential than we are with logs, I would assume. So every time you're looking at a log, you have to think about the exponential function, and the input becomes the output, and vice versa. So now for number 4, I have that log base 10 of 1 equals what? So the base, so the exponential form is going to be with base 10. So 10 to what power gives you 1? I know that any number to the 0 power is 1. So 10 to the 0 equals 1. So therefore log base 10 of 1 is 0. For number 5, the base is 10. So 10 to what power gives me 0.001? Well, I can write 0.001 as 1 over 1,000. And in exponent notation, this is 10 to the negative 3. So therefore, 10 to negative 3 gives me 0.001. Put it in your calculator. What is 10 to the negative 3? It's 0.001. So therefore, the answer is negative 3. So you see the result that I'm getting from evaluating a log. It's an exponent that the base needs to have in order to get this value. Remember we encountered E. E is the Euler constant. It's just a number, an irrational number, just like pi, and its value is like 2.714 and ... right? So if I wanted to write this in exponential notation, the base is E. So I'm saying E to what power gives me E? Well, this is E has to be E to the 1 gives me E, right? So log base E of E is 1. All right, so we're mostly going to work with base 10 and base E. So when we have base 10, we call the logarithm base 10 the common logarithm, and we simply just don't write the base anymore. So for example, if you have log of 1,000, it means that the base is 10. It's just not written there. So when we don't have the base, when the base is not specified, it means that it's 10. So log of no base of 1,000 means log base 10 of 1,000, and it's 3 because 10 to the third equals 1,000. Now when the base is E, we call the logarithm natural logarithm, and instead of writing log base E, instead of specifying that the base is E, we're simply going to write ln instead of log base E. So ln of z means log base E of z. So from now on, when you're seeing ln of something, that means that the base is E. So for example, ln of E is 1 because E to the 1 is 1, right? So notice that this is the same as this right here. Okay? All right, so if we wanted to graph logarithmic functions, we're basically just going to put it in the calculator. So if I wanted to see how log of any base looks like, in this case, in the first example, we saw that this inverse right here, it was for log base 2 of x, right? Because this was the inverse of f of x equals 2 to the x. So now if you want to graph any logarithmic function, basically in your calculator, if you pull out your calculator, you see that you only have log and ln right there. So then let's graph the log function with base 10. You turn it on and you go into y, and you're going to put log and then x, and then hit graph. You probably have a wrong window, so we're going to go to window, and we know we're going to start at 0 and end at 10, and then let's go from negative 10 to 10. And then hit graph. So you see how it looks like. It looks exactly like what we had earlier. So it's going to be something like this. Okay, so this is log of x, which means if the base is not there, it means that it's base 10, right? log base 10 of x. So the domain of log of x is 0 to infinity. Notice that I only have y values for positive x's. And then the range is, notice that this goes all the way down to negative infinity, and this is going to slowly increase up to positive infinity. So the range is all real numbers. All right, just like we have rules for exponents, we're also going to have some rules for logarithms. So one of the first rules for exponents was that a to 0, so any number to 0 power is 1. So how does that translate in logarithm form? So the base of the log is going to be a, and then the input is going to become the output, and then the output, the 1, is going to become the input. So the first rule that we have for logs is that log of any base of 1 equals 0. And this is because a to the 0 equals 1. The next one, a to the 1 equals 1. Well, how does that translate in log? Well, the base is a, so it's going to be log base a of the input is 1, so it's going to become the output, and the output was a, so it's going to become the input. So log base a of a equals 1, and this is because a to the first power is a. Now recall that we said that the logarithm functions and exponential functions are inverses of each other. So if I take the input x and I apply the exponential and then I apply the logarithm, they're basically going to undo each other. So when I have x and I do logarithm of x with base a, and then I do exponential with base a, basically the answer is going to be just x. So a and log base a of x, they undo each other because they are inverses. So the input is just x. Similar when you have log first and then exponential with the same base. Okay? Now, we had rules that told us that when you have, for example, 2 to the x times 2 to the y, we keep the base and we add the exponent. Similarly, we're going to have rules for logarithms. So when I have logarithm of base a of a quantity big A times big B, then this is going to turn in logarithm of base a of the first quantity plus logarithm of base a of the second quantity. And then when we have logarithm of base a of a divided by b, so something, whatever your a is, a can be x plus 2 and b can be 200. So when you're taking log of a quantity divided by another quantity, this is going to turn into log of the first quantity, so log of the top minus log of the bottom of the fraction. Okay, so these are rules that you're going to have to remember in order to solve any problems with logs. But the most important property that we're going to use is this one. So basically, this rule says that when I have log of a base of a quantity and that quantity has an exponent, this rule says that this exponent is going to come down in front of the log. So log base a of a to the x is going to turn into x times log base a, base letter a of a. So for example, if I have, let's do an example in here, log base 2 of 3 to the x, this rule allows me to pull the exponent down in front of the log. So this is going to turn into x times log base 2 of 3. Okay? This property is very important because every time we want to solve problems that the unknown is at the exponent, that have the unknown as the exponent, we're going to have to use this rule to bring the exponent down and then solve it, because we are comfortable solving when x is just regular, it's not an exponent, right? So We had a homework problem that said that after T days, the amount of thorium in a sample is given by this equation, and you are asked to find when the amount, okay, this doesn't make any sense in here. You're asked to find when the amount halves. So the question is, when the amount of thorium halves. I think that's how you spell that. Don't take my word for it. Okay, so basically you start with 45 micrograms, and then you're asked to find when. So when, that means that we need to solve for t, and notice that t is an exponent. So how do we solve that when it's an exponent? We're going to have to rely on logs. So I'm asked to find when it halves. So half of 45 is going to be 22.5 equals 45 e to the negative 0.029 t. So I'm asked to solve for when, so I'm asked to solve for t. When, for what t is the amount equal to 22.5? All right, so our first thing that we have to do is we're going to divide by 45 both sides. Okay, so the 45 and 45 goes away. So then we're going to have 22.5 over 45 equals e to the negative 0.029 t. Now, since t is an exponent, what I'm going to do, in order to be able to bring the exponent down, it has to have a log in front of it. Okay, so you can't just bring the exponent down. You have to apply the log with that base. So since the base of this exponential is e, the inverse function that is going to undo the exponential with base e is the ln. So what I'm going to do is apply ln on both sides. So I'm taking ln of both sides. Okay, I'm taking ln. If I'm doing something to one side, I have to do it to the other. So then I have that ln of 22.5 over 45 equals, now I can bring the exponent down. So it's going to be negative 0.029 t times ln of e. But ln of e is just 1. So therefore, I'm going to divide both sides by negative 0.029. So this is going to go away with that, and all I have on this side is t. And then on this side, I'll have ln of 22.5 over 45. Everything divided by negative 0.29. Finally, sorry about this. I need to leave more space. Finally, t is going to be equal to ln of 22.5 over 45, everything divided by negative 0.29. So this is the exact answer. This is the exact answer. And now to get an approximation, we're basically going to put that in our calculator. So t is going to be equal to, let's put it in our calculator. So it's going to be equal to, I'm going to put ln of 22.5, divided by 45. And then this is divided by negative 0.029. So then the answer is 23.9. So let's say 24. So this is approximate 24 days. So this is the approximate answer. So we solved for a time t, and it was given as an exponent. So every time the thing we have to solve for is an exponent, we're going to have to use logs to bring the exponent down. Basically, we're using this important rule right here that allows us to bring the exponent down in front of the log, okay? All right, so let's take a break.